Okay, now that we've talked about molecular shapes, we're going to talk about molecular polarity. And molecular polarity is important because it tells us how molecules act. How do they act with respect to each other and to other compounds? Okay, in order to do that, we need to probe dipole moments. Now, dipole moments arise from the difference between electronegativity between atoms. All right, so if you have two atoms and they're pulling on the bonding electrons differently, then the electrons are going to spend more time around one atom than the other, and so you're going to get a disparity of charge, and that makes a polar molecule, or at least a polar bond. Okay, so induction is when other electrons around it are affected by the dipole moment. Okay, so we'll be talking about induction a lot this semester. Right now, let's just start out with a rudimentary definition. Okay, now a dipole moment is got actually a physical definition for it, and that is the amount of partial charge times the distance that the partial charges are separated. Okay, so a dipole moment, they're reported in the units of debye, and I'm going to walk through this math here with you, but I will say this: it is not critical that you deeply appreciate this. There is a superficial message that we need to get from this, and so I ask you to watch out for that as we move along. Okay, so let's go on to the next slide. Consider the dipole that is carbon, let's see, methyl chloride. Okay? So if it's methyl chloride, then the dipole moment, well, this is always the definition. The methyl chloride is going to be this is the dipole moment right there, mu. It's the charge times the distance, right? This is just a physics definition. And can you see a red arrow here? Can you see a plus sign at the tail? Okay, the plus sign at the tail goes to the element that is more electropositive. So we go and look up the electronegativities of these two, of carbon and chlorine. I find the carbon is less, and so I put an arrow toward the chlorine, and that tells me where the dipole moment is. Okay. So the dipole moment then is calculated as the charge, and the charge happens to be in these units right here. Can you see that? And here's the length of the bond. Okay? Now, it turns out that it's not a full charge because this is not an ion, right? This is actually a covalent bond. So it turns out there's partial charges here, and that gives us this charge difference right there. All right? So the dipole moment of this particular molecule is 1.87 debies. I've never heard anybody pronounce that. Maybe they say Dipole, I don't know. So I'm going to call it debies. That's what I've always called it. 1.87 debies, and that gives us some measure of how polar this molecule is. Notice I did not tell you where this number comes from. I sort of hinted at it, but didn't say it. I did say where this number comes from. We're not going to be doing a lot of calculations, so I want to broad brush that. I want to come out and say that in the end, we can quantify how polar this molecule is by giving it, by subjecting it to this physical relationship, and we're going to get a number called 1.87 debies. Okay. Now, if that bond were longer, then you can see that would make this unit go up, and the dipole moment would go up. If the charge difference was bigger, then it would also go up. All right. That's what this is about. So we'll be looking up tables occasionally, not a lot, to quantify how the dipole moments of particular molecules, and so hopefully that'll have some meaning to you. The main point we have not stated yet, okay? So we're coming to that. I'll state that at the very end. All right. Now, what would the dipole moment be of methyl chloride if it were 100% ionic? Well, then we would take these two charges, and it would give us the difference between those, and it would be 4.8 times 10 to the negative 10 ESUs, which I'm not going to get into what that means. And here's the bond length, and it would be 8.51 debies. So that tells you how ionic this bond is, right? Because if it were purely ionic, it would be 8.51 debies. In fact, it's 1.87 debies, right? And so that tells us how ionic that bond is. All right, it's a little bit misleading, I think, to say that the bond is ionic in character, but that's a term that everybody uses, and I think it's fine. Okay, so it's 22% ionic. We're not going to be calculating a lot of these. I think it's helpful for you to see it. Okay, Now, for molecules with multiple polar bonds, aha, that's a separate issue now. So take DCM, dichloromethane. Here's dichloromethane here. And if you've got a carbon-chlorine bond here, it's got a dipole moment going in that direction. This carbon-chlorine bond has got a dipole moment going in that direction. You see, they have some constructive interference, right? They're both sort of pointing in that direction. Can you see that? They're both sort of pointing that way, right? But there's also some destructive, right? They're sort of pulling against each other too. So what we have to do when we evaluate the polarity of a molecule like that is we have to say that it's going to be the sum of these two vectors, right? Now we could do that with math. We're not going to. That's just simply a trigonometry question, right? We would set up a couple right triangles here. We would see which parts were subtractive, which parts were additive, and we would say that's our resultant vector, okay? Calculus has got some even more useful tools for how to do that. But we're not going to do that. We're simply going to say, yeah, I can picture how there's a resultant vector that goes in that direction. Now here, can you see with nitrogen being the more electronegative, these hydrogens are all pointing in that direction. Can you see that they're all going to have sort of an upward dipole moment? And so if you add all those together, you're going to get a dipole moment going in that direction. And the same thing goes for water. You get a dipole moment of that bond. This is a polar bond. These electrons are also, right, pulling in that direction. So we're going to get a net dipole moment in that direction. All right. Now, you notice that I invoked the molecule's geometry in order to be able to tell if it had a dipole moment. So it's critical. As I said in our last conversation about molecular geometry, we have to know the molecule's geometry before analyzing its polarity. In this case, you can see if this were planar, and if these three hydrogens all oppose each other, this would have a net dipole moment of 0, right? But the fact that we've got this lone pair of electrons there, pulling the electrons in that direction, aha, that gives it a net dipole moment. Okay? Let's not deal with these questions right now. Let's move on. Keep this video short. All right, we oftentimes illustrate molecular polarity by using something called electrostatic potential maps. Now, you're obviously not going to have to make one of these, but it's really useful to be able to recognize what's going on. So what we do is we'll say that the most negative is red and the most positive is blue, right? And so if I've got sort of an uneven sharing of these electrons across this bond, what's going to happen is the electrons are going to go toward the more electronegative element, and so you're going to get more red up here and more blue down here, which is you've got your, your paucity of electrons down in that end. All right? So let's look at some molecules, and just to get some kind of an idea, the dipole moment of acetone is 2.69 Debbys. Can you see why? Because you've got 2 bonds here, and that oxygen is very electronegative, so it's pulling the electrons that way. What about chloromethane? We already said that. It's 1.87. Water, 1.85. It's not necessarily intuitive because we've got a couple polar bonds there, right? Can't really tell why it's 1.85, but this gives you a sense of how strong those poles are, or how heavy those poles are. Okay, what about methanol? 1.69. So this kind of table is going to help us choose solvents for particular reactions that we want to do later. And look at this over here. Pentane, where that bond is almost completely evenly distributed, it has a dipole moment of 0 Debbys because there's just no polar bonds in here. But what about carbon tetrachloride? You've got 4 polar bonds of carbon-chlorine polar bonds. And so the question, you would think it would be like extra polar, right? Because of that. But don't forget, in a perfect tetrahedron, those 4 bonds oppose each other, and we end up getting a 0 dipole moment. So it turns out carbon tetrachloride is actually a nonpolar solvent. Okay? So that's a brief introduction to dipole moments and molecular polarity.